right. Great. Hi, everyone. Thank you for having me. I am Annmarie Eldering at NIST, and I am at the NIST in Gaithersburg, Maryland, not that fancy one over there in Colorado. And I want to talk about two topics. One, brief introduction to what we've been doing with this consensus standards work, and then also the newest thing is we have some results from an effort with EMIT data and an intercomparison activity. So that's what I'm going to share with you today. I have a long list of folks here on this first title page. They were all part of this work to write a report about current practices. And then the EMIT effort has been with a different crew, but also a large crew. So just want to acknowledge, I am just, data gatherer, meeting caller, do a little bit of analysis, but it's all these technical teams that are participating that makes this actually happen. We can't do it if people don't want to get involved and work with us. But everyone who's attending these seminars probably knows this, but just to get us on the same page, there's a lot of really new exciting stuff happening with the methane plume work these days, new measurement data sets all the time, lots of demonstration of finding methane plumes. And as you know, we have a mix of things like federal, NASA, other space agencies putting up instruments, and some of these are the traditional larger instruments. We have smaller instruments like EMIT going on the space station, private companies, nonprofits, like there's a lot of folks participating. And so it's a really exciting time to be working on this topic. But also it's sort of, we're discovering and we're trying to get users involved, and there's action happening that's sort of pushing us towards an operational like data product. But when you look at data right now, you see a lot of variation when different teams look at the same data set or different instruments make measurements. The controlled releases are really key, which we'll talk a little bit about. But I think there's a role for someone like myself coming from this standard setting organization. I did work at NASA for 22 years. I worked in the remote sensing. So I have knowledge of that. And now I'm learning from my NIST colleagues about the standards. So hopefully bringing the two ingredients together. And what we've been trying to do here at NIST is we started by just kind of doing some brainstorming stuff a while ago, and then we have developed some written definitions and terminology, documented the current practices, and now we're doing intercomparison. And we like to daydream too, where could we go? I mean, you could imagine trying to use this kind of approach with some fence line monitoring, try to actually provide some guidance about the validation practices. We are working with the GHG Center. So there's other directions we could possibly be moving in. Although one of the things that I like to remind people of is, we're a pretty small group, so I have to think about what can we actually get done given who and what we have, and how do we maybe just make sure we have good connections to others. So right now we're pretty focused in what we're doing because we just don't have a massive amount of personnel to work on this. And just in case people don't think about NIST day in and day out, when you think about our National Institute of Standards and Technology, remember that standards means a lot of different things. Back in the old days, right, we had a meter standard, or we had a weight that was a kilogram. A lot of that has transformed. Now we keep time based on the frequency of an atomic molecule vibration, right? We have atomic clocks. We do other things in a more advanced way. So we have physical artifacts, but we also have reference materials. So if you're a manufacturer of, say, peanut butter, you might have a NIST peanut butter reference standard, and you compare your product to what the reference standard is. And for work like this, it's really about consensus standards, like understanding what everybody's doing, documenting it, trying to develop some consensus about what the right approaches are. So standards has a number of different meanings depending on the activity. And another thing folks don't always know about NIST is it's really a very collaborative agency. We don't do the work all just here. We try to connect with industry, researchers, practitioners, and really bring in all the experts to the conversation. So Just wanted to highlight that, we're working with all different kind of groups, folks who make measurements and analyze them, people who just take measurements from others and analyze them, folks who aggregate the data, and we're trying to think about all these end uses where the data might be useful once methane plume products are produced. So that's just a mindset I wanted you to think about of how we're trying to approach this. All right. So I almost took this slide out because I'm sure you all know it, but just so we're on the same page, the thing we're talking about today is where folks collect hyperspectral data measurements, and this is an EMIT data cube example. Use a match filter to try to find column enhancements of the methane, identify what pixels are in a plume, and then in most cases, the focus of this work right now is on people who are using the integrated mass enhancement approach to then estimate what emission rates are. So this is the general process, and it's important to realize that there's many steps along the way, and you have to make some assumptions. There's inferences. You're trying to determine a number based on a field that you have that's not perhaps the most direct measurement possible. So it's not surprising that in this remote sensing problem, you're going to have variation in choices and variation in outcome, very typical of these types of measurements. So I talked about this document that we created. We had a whole bunch of conversations after our workshop so that we could really understand how people do the data analysis, where they're making choices, what's similar, what's different across teams. And we wanted to put this in a place where folks could find it. So it's at this moment in time, you can actually find it in a NIST interagency report called Common Practices for Quantifying Methane Emissions from Plumes Detected by Remote Sensing. And this will also get released through CEOS, the Community on Earth Observations from Space. And eventually we'll revise our version, so whatever editing happened, these two will match each other. But right now you can go on the web and find that NIST report. So that's sort of a first foundational document that we created. And now we've moved into what I think is even more fun, is looking at data in detail. So what I'm going to share with you today is some of the results we got from an effort to look at EMIT data with 8 different teams. And we have 4 scenes that I'll describe a little bit more, and 8 different teams working on this. And we looked at a different number of different products from folks, the plume, mask, what kind of stuff did they use in the winds, what their emission rates were, etc. And these are the RGB images from EMIT that Andrew Thorpe provided for our 4 different scenes. And what I want you to get out of this is that you have a couple of these that are over a fairly bright desert type surfaces. Scene 3 is not quite as bright, and you have some features like these. I think this is a riverbed that you can imagine might provide some confounding surface properties. And then scene 4 is very heterogeneous. This is actually in an urban setting. So we've got different types of surfaces that we're dealing with in the 4 scenes, as well as different emission sources and emission rates. And there's a lot of words on here. You don't need to understand all of them. So these are the 1 and 2 are in Turkmenistan, not exactly the same location, but close to each other, Wyoming and in Mexico. And what we'll discuss today are emission rates that are estimated to be somewhere in the 1,000 to 15,000 kilograms per hour. So just in the context of the type of work that people are doing, remember that you have everything from plumes of the size we're talking about today to some new instruments that are detecting things in the hundreds of kilograms per hour. And then you have aircraft instruments that are much smaller, that, a few kilograms per hour. So there's a very wide dynamic range of methane plumes that people are looking at, and we're today talking about the pretty big ones. And we asked folks to provide a certain set of data to us. And one thing I want you to get out of this is the variety of the level 2 or the match filter results. So we had all teams, we asked them to look at the analysis using the JPL provided level 2 data. So that way they're all working off of one uniform product. And then for some cases, people were able to derive their own level 2 from the radiance field. So we have that different set of data. And then we actually used what we call a mix and match experiment, thinking about what might somebody be working with if they're just a data user at the far end. And there they might have folks providing something based on L2 and then different teams providing it on their own. So they have a mixture of products that they might see, and what are the statistics of those kind of data sets. And we got lat long of the plume, wind speeds, effective wind speeds, L, IME, emission rates, uncertainties, and that's all the stuff we've digested and I'll share with you today. And so this was just me telling you what I was going to do, looking at did they detect a plume or not is sort of the first question, just plume detection. What was the scatter of the origin? How do the emission rates compare within uncertainties? And can we do some experiments where we keep a term constant and then see how that changes the results? So let me just dive in now to some of the results. These are just images where I've mapped all the plumes that were provided to me. No team identifying data, but just to give you a sense of kind of things that we saw. So scene 1 and scene 4, you only have one plume detected by each team. You can see here, this one has a scale that runs is 10 kilometers is this length. And some teams determined that the plume length was sort of about that size, while others have plumes that extend many times that. So big variation in sort of the area covered by the plume. This case is on a much smaller scale. You have sort of 4 kilometers, and it's a blobby plume. Some of folks' blob is, somewhat constrained, and then some folks it's pretty big. These are more complex situations. In scene 3, with a scale of about 8 kilometers, there was one large plume that all the teams detected, and I'm pretty sure everybody also detected the smaller plume. But in scene 12, we have a lot more variation. We had some teams reporting that there were 12 plumes, some teams had 16 plumes. You can see, you might have something here that teams might see as 2 different plumes, but somebody else thought it was just one big agglomeration of a plume. So there's variation in the detection, particularly for scene 2. And in this case, what we did was we just tried to look at all the data that was provided and say, okay, what is anyone who's identifying a plume sort of in this region, we'll pair those all up and do the stats on that, do the stats together. And there were some things like this giant one that was harder to integrate an analysis because it was sort of different from what everybody else saw. Again, a word chart. What I want you to remember, you'll see some bar charts later, some box and whiskers. So scene 1 and 4 have a single plume. Scene 3 has 2, and then the majority of the bars are from that scene 2 with a complex set of plumes in it. So we looked at the plume origin as the first step. This little map in the lower left just shows you the data that was provided to us. If we map it out, you can see the plumes are in different locations. This blue bar is about 20 meters. So this is, scattered maybe 100 meters east to west, a little bit more north to south. In talking to the teams, we realized that some teams might identify a plume, but then look at this imagery, this visible imagery, and they might say, oh, hey, it looks like this is probably where that plume is coming from because there's infrastructure, so they'll drop their pin there. Other teams will just look at the data without referring to the underlying image and drop the plume where their algorithm finds, say, the highest concentration in the IME or some other feature they determine. So that leads to some scatter in the location of the origins. And we decided it wasn't that useful to look at it in lat long space, so we decided we would rotate it to along the direction of the plume or where the wind was carrying the plume, and then across the plume. And one idea we had is that, if you have a plume that's got fairly well-defined edges, you should be able to locate it across plume pretty well and maybe you'll do less well along the direction of the plume. Statistics don't really tell that story. So these are box and whisker plots for that plume origin, where I've just taken the mean of everybody's result and then developed statistics around that. So the X's are the mean, the bar in here is the median, and then you've got the 25th and 75th quartile, and then the full data distribution included. I've put dashed lines here at about the width of a single emit pixel. So an emit pixel is 60 meters. So I have 60 meters up, 60 meters down. So you can see most of the data falls within 1 or 2 pixels. That's true both along wind and crosswind. The crosswind statistics aren't actually particularly worse than the along wind for this case. So I don't know that our theory about it being easier to locate along versus across was really true, but we have this like now some indication that you're sort of 1 to 2 pixels is the kind of error you're seeing in the origin location or the variation you see. And here's just a quick summary on the variation of the emission rate estimates in kilograms per hour here. We had a whole collection of plumes that were less than 5,000, and so these bars look small, but again, you know, you still have variation of maybe 50 to 100% across the teams. Some of the very large emissions can be quite scattered. For example, here you've got estimates that in the 25th to 75th percentiles range from 7,000 to over 20,000 kilograms per hour. So some cases have a lot of variation, some less so. And then there's uncertainties assigned, and you just generally see the pattern that these uncertainties can be quite large, especially in the cases where the emissions are large. And I did just a simple plot here where we looked at what percent difference from the mean do we see, and wanted to find out if, you know, something like emission rate was a driver of that. And I think the conclusion here is that's not like a strict driver. You can also say you see sort of minus 50 to over 100%, sometimes sort of plus or minus 50%. So that's an idea of what kind of variation we have in the results across the teams for these particular cases. And one of the things that we worked on a bit, especially with help from Alana on the Carbon Mapper team, was to try to think about this equation that's used for the emission rates and look at the enhancement equation and think about where are the variations potentially coming from. And then could we hold the term constant and see if that really explains what the variation is? So, you know, wind speed's an obvious term. It comes in directly to the equation. The retrieval informs the enhancement. And then, you know, quantification method is everything from what pixels do you include, the characteristic length, your transformation of wind speed into U effective. That one's harder to hold steady, but we have to think about all of these as potential contributing factors. So you'll see a chart in a few minutes about the variations and the tests we did to try to hold parts constant. And just a minute to talk about relating U10 to U effective. So Daniel Verone made a chart for me showing the relationships that were used by the different teams, and here are the actual equations. And so the things that I think we see here are that teams have a variety of equations, although for, you know, these moderate wind speeds, the actual values are not that different. Some teams are not using a transformation, they just use U10 in their results. But you have to remember that this development of the equation is done with a simulation set. It's related to how they define this characteristic length L. It's related to their match filter. So it's not like one is right and one is wrong. It's that this is developed to fit in the framework that that team is using for their data interpretation. But it helped us sort of think about how big is the variation, and if you swap one equation for another, you know, how much of a change is that going to be in the effective wind speed? And if we look at the input winds and the U effectives that were applied, folks are grabbing wind data from different sources, so you do already have just variation in the wind speed for that time and location. You know, for a lot of these cases in scene 2, it was mean or median around 4 meters per second, but it ranged from 3.5 to 5. And then scene 3 and scene 4 had the somewhat lower wind speed U10 values. And then this is how those get transformed into U effective. So it gives you some sense of the scatter that exists in the wind fields that are used. And then I mentioned that characteristic length is another piece of the equation. So just sharing some of the data that was used in the analyses. Again, definitions matter here. So you do have wide range of values. Not saying one's right, one's wrong. It sort of depends on how it's used in their interpretation. And here's some actual comparisons of data. So for scene 1, these are the 8 different results that were submitted, and the orange we're showing you just the data as submitted. So everyone had an estimate of emissions. You can see it ranges from like 1,000 kilograms an hour to over 6,000, with the uncertainty bars indicated. And in this case, actually, a lot of the data agrees to within the uncertainty bars. So one could argue, you know, they're telling you the same story when you think about the uncertainty. The orange bars, which are the same case here for scene 4, that blobby plume, also agree within the error bars. The values range from like 4,000 to 10,000, but the uncertainties are quite high, right? This is sort of a estimate of 10,000 plus or minus 5,000. So we know it's not been all that well characterized. The other bars on these plots are where we held the wind speed, the U10 constant, and then recalculated what the emissions would be. And so for a couple of teams that boosted up the emissions, for some teams it was a slight reduction or only a slight change. Didn't really change the stories. Things agree to within the uncertainties. There's a little more scatter. For the case of the blobby plume in scene 4, the wind speeds were fairly low, and it turned out that changing them didn't really change things all that much. You maybe get slight improvement in agreement, but overall not a huge change of the story. So in some ways we're like, well, then the wind speed itself is not the sole driver of variations across the team. So we calculated the coefficient of variance, or the standard deviation, divided by the average, first for just the base emissions, and then when we put the same wind speed in for everybody's results. And the key thing you see here is there's 2 cases that have a coefficient of variance over 50%, but the majority of them are sort of 20, 30 to 50% coefficient of variation. Changing the wind speed dropped it in some cases, but increased it in others. So it wasn't a uniform change in one direction. And the overall story is not that different, that it's sort of 20 to 50%, even if everyone had the same wind data. We did try to look at the influence of level 2, and this was a little bit hampered by trying to get all the same groups of data wrapped up and identified. So there's less plumes that are included in the analyses. We do see that they're somewhat smaller coefficient of variation when you look at their across the bar, right? Like case 10 is somewhat lower when it's on the same L2 as compared to the standard submissions. If you then also make the wind speed, you would hope that, oh, we have all these factors that are the same. Sometimes that lowered the coefficient of variation, and sometimes it didn't. And it's hard, remember, these all look pretty small, but these are also almost all cases that had fairly small coefficient of variation. So, you know, so small data set, we can't really make generalizable conclusions. It was just like, oh, this might be something worth looking at further or in larger data sets. So here's my killer word chart. We're almost at the end. I think the big gain we made with this work was really practicing, bringing our group of 8 together, getting in data sets, working up the analysis, sorting through the plumes. I have to say we've done this now with a new set of data, and by having better processes, it's been much faster to get the analyses done. So we gained some from that. We had a lot of great discussions to learn about how people were doing it and people's ideas of what were some key factors or what we might be able to conclude or not conclude. So I don't think we're ready to like close the book on it. I think we've learned some things about the variation we saw, but we do have to remember these are some very long, physically long plumes, large emission rates. So we want to go look at other types of cases and see what we see in those. And also just want to acknowledge, like, this is one activity in a whole set of things that's happening. It's been great to have the support of all the different teams and working on it, but I know there's other activities like Medusa happening in Europe. That's been a great organized, larger effort to really look at the methane plumes and the methods that are in use. Thank you to Stanford and University of Michigan. I forgot to make that edit, but these controlled releases are just awesome. And we started actually digging in some Nmap data. So we're excited about what we can do with that data set. And then I don't know if we have any of the Colorado folks here, but Dan and Ezra have shared that they've also got their controlled release facility ready to roll. And they're going to be able to have releases in the sort of 1 to 2,000 kilogram per hour. So that's going to be a great additional resource to the community as we try to learn more about this, this kind of data product. So I'm trying to get this out as an interagency report. We've also got some cool Nmap data. I'm glad I got to present this stuff to you now. I think there's some question marks around how far we can get this rolling, just because the efforts in the greenhouse gas area are not really aligned with the administration these days. So it's unclear to us what's going to happen next fiscal year. So we'll try to get reports out and data in people's hands. Not making big plans for the next year, but just trying to wrap up what we got underway. But fortunately, because this is done with a big group of partners, hopefully these messages can be carried out and brought to different meetings and discussions, even if I'm not the one doing the discussion. That should be it. Thank you, everyone, and I'm happy to hopefully got some good time for discussion now. And then if you want to track me down, Annmarie.Eldering@NIST.gov. So drop a line. Thank you, Evan.
Oh, thank you, Annmarie.